This screencast is on determining empirical formulas through combustion or by combustion analysis. So first we're going to start off with what combustion analysis is. And in combustion analysis, we're going to take some sample, some compound, and we're going to put it inside of a furnace where we're going to heat it. And then oxygen is going to go through the furnace, and this compound, usually it's a hydrocarbon or a hydrocarbon containing oxygen or nitrogen, it's going to react with the oxygen. So you've got the O2 reacting with the sample to produce H2O and CO2, and sometimes some other byproducts. But the H2O and the CO2 are the really important parts, because these absorbers here will trap the water and trap the CO2, and they're going to increase in mass. And we can calculate how much their mass increases, and from that we can figure out the amount of hydrogen that was in the original sample. So we can figure out how much hydrogen was in the sample, and we can figure out how much carbon was in this original sample. And that's going to help us work towards the empirical formula. Let's look at a sample problem. And these problems aren't really hard, but they take a while because there's a lot of steps. So for step A here, we're looking at a compound called ethyl butyrate, which makes pineapple smell pineapple-y. And it contains basically three elements: carbon, hydrogen, and oxygen. And if we combust 2.78 milligrams, we're going to get this much CO2 and this much H2O. So since we're dealing with masses, the first thing that we're going to do is convert the masses of these substances to moles. So I'll explain how we do this. We're going to start off with 0.00632, because that's milligrams, so grams of CO2 in that case. And then multiply divide by the molar mass to get moles of CO2, and this is the molar mass. So here's our value for the molar mass: 1.44 times 10 to the negative fourth moles of CO2. And notice that there's one carbon in CO2, so essentially that's going to be the number of moles of carbon that was in the original compound, because that's where the carbon came from. Remember, we only reacted with oxygen, so this carbon must have came from the original compound. Same thing with the water. We take 0.00258, that's 2.58 milligrams of H2O, convert it to moles by dividing by the molar mass, which is 18.02. And then once we've got there, we're going to add another step here, because there's two moles of hydrogen, or two atoms of hydrogen. In every 1 mole of water, there would be 2 moles of hydrogen. So I'm going to put 2 moles of H2 up here, or of H, and then 1 mole of H2O down here. So that when I finish this, what I end up with is 2.86 times 10 to the negative fourth moles of H. Okay, so now I've got my moles of H, my moles of carbon, but there's also some oxygen in this substance. So we have to work backwards to figure that out. And what we need to do is calculate the number of grams of carbon and hydrogen I had. I'll show you how we're going to do that here. We're going to go with these values and just multiply them really quickly by the molar mass. So 1.44 times 10 to the minus fourth moles of carbon. We know that 1 mole of carbon weighs 12.01 grams. And so in this case, we end up getting 0.00173 grams of carbon. And down here, we're going to get 2.86 times 10 to the negative fourth moles of hydrogen. Multiply that times the mole ratio, or the molar mass of hydrogen, which is 1.01 grams of H per 1 mole of H. And what we end up with here is a really small number. This problem's kind of difficult just because it's milligrams, but it's not that bad. Grams of H. All right, so check this out. If I add these two up, the carbon and the hydrogen, what I end up with is I end up with 0.00202 grams. That's the mass of those total. But I know from the problem that I have 0.00258 grams, I have 0.00278 grams total. So that would include the carbon, the hydrogen, and the oxygen. This is just the mass of the carbon and the hydrogen. So the oxygen's got to be the difference. So if I put 0.00278 up here, and I take the difference here, this is going to give me the mass of the oxygen, which in this case is 7.6 times 10 to the negative fourth grams of oxygen. And real quickly, I'm going to go ahead and multiply that times my mole rate, or not my mole ratio, I keep saying that, times the, divided by the molar mass, so 16 grams of O, 1 mole of O. Grams would cancel when we multiply these out, and I'm going to end up with 4.75 times 10 to the negative fifth moles of oxygen. So I jumped forward here just a little bit to save time in the video, and I just took the moles of carbon, rewrote them down here, moles of hydrogen, and moles of oxygen, and wrote them all down here. So I can figure out what the ratio is between all these elements, because that's really what an empirical formula is, right? So I'm going to divide this by the smallest one, which is 4.75 times 10 to the negative fifth. And obviously for this, I'm going to get 1. Well, if I divide the other ones by this same value, so 4.75 times 10 to the negative fifth, and 4.75 times 10 to the negative fifth, what I end up with is right about 3, right about 6, and 1 for this particular value. So that tells me that the ratio is 3 carbons to 6 hydrogens to 1 oxygen. That gives me the empirical formula of C3H6O. And so now I know how to do the empirical formula for this particular compound. All right. Now, part B is a little bit more difficult, but it follows the very same process. So what I'd like you to do is to try to figure this one out. Go ahead and solve it on your own, and then you can press pause on the video, and then I'll have the answer worked out for you in just a minute. So I went ahead and wrote down the answers in this one. So I jumped quite a bit ahead just to make sure that I didn't want to waste the time of you having to actually watch me type all this out. But I'm going to go, or write all this out, but I'm going to go through it. So stepwise, procedurally, we just did the same thing. We figured out the moles of carbon. Okay, so there's our moles of carbon by converting by the molar mass. And then we figured out the moles of hydrogen. Again, we had to get to moles of water and then double it because there's 2 moles of hydrogen per 1 mole of water. We got that value here. Then I multiplied these values for carbon and hydrogen by their molar masses just to get the masses, and added them up to get the total mass of the carbon and the hydrogen. Sorry about that bell there. And then I got this from the problem. It's the actual sample of the substance here, which is 5.250 milligrams, which is the carbon, the hydrogen, and the nitrogen. And so the difference between these is 9.2 times 10 to the minus fourth grams of nitrogen. Convert that to moles, and now I have moles of nitrogen, moles of hydrogen, and moles of carbon. All right, next step is just to look at the ratio between the two, which I did down here. And looking at the ratio here, I divide the moles carbon and hydrogen by the moles of nitrogen because it's the smallest one. And I do that because that will always produce whole number ratios, and I get 1, 5, and 7. So this is the empirical formula. But this problem actually asks what the molecular formula is, so I need to be careful about it. It says it has a molar mass of 160 plus or minus 5 grams per mole. Well, if I figure out the molar mass of this compound, it weighs 81 grams per mole. So in looking at that, I have to, so if the molecular formula has a molar mass of 160 grams per mole, the molecular formula for this compound must be double that. So the molecular formula would be C10H14N2. So that's how you work from the empirical formula to the molecular formula, is by looking at the molar mass of the molecular formula and see how it relates to the molar mass of the empirical formula. I hope that helps with determining empirical and molecular formulas through combustion analysis.